Okay, here we are at chapter 10, the lecture slides on springs. Um, as you can see from this opening graphic, there's a lot of interesting, uh, lot of interesting springs out there. This chapter doesn't really deal with the specifics of a lot of the springs pictured here, but it kind of gives you an idea of the potential here in this first graphic. Let me get to the draw tool. We have a variable coil length, right? So this is a variable coil pitch, I should call it. And that'll give you a nonlinear behavior. This is a two springs, one packed inside the other. This will give you a heavier stiffness without any increase in the package size. Here, instead of variable um, pitch, we have variable coil diameter. Usually this is done to give you a different stiffness as springs collapse. And down here we've got some leaf springs. So these are not coil springs, but they're leaf springs. There's all sorts of springs that aren't coil springs, just to make you aware. As in fact, I consider anything you can push on that deflects to be a spring, which is everything in the universe pretty much except for a vacuum in space. Um, even air can be a spring, right? So if you have, so I'll put the here, even air can be a spring, like a pneumatic cylinder. So if you have a pneumatic cylinder and you have a piston in here that's nicely sealed up, and you have a rod and you push on it with some force and you have trapped air, the air will indeed act like a spring in this case. So, like I said, just about everything except for the vacuum of space is a spring, including gases. Fluids are virtually incompressible, a lot of them. Them not so springy, but they do have a tiny amount of springiness with an incredibly high spring rate. But other than that, just about anything is a spring. We're going to cover most of this in this chapter, um, except this part here. Mercifully, I'm eliminating the fatigue of springs. We'll get into that later as to why. But we're going to start with the simple here with helical coil springs. They're typically made out of round wire, very specific wires, not just any wire. Can't be stuff like copper wire, things that are a little too malleable. Um, Usually steel, but not exclusively. Um, so the neat thing about this graphic right here is if you take this spring here on the left and just cut it anywhere, like let's cut it right here, and do a free body diagram, you see that in order for this thing to be in static equilibrium, we need a shear force and a moment. And it's actually this moment right here that's doing all the spring action. So the spring action is virtually 100% due to this torsion. So let me explain what happens when you pull or push on a extension or a helical coil spring. Essentially what you're doing is twisting the wire as per this torque that's being applied. The shear force isn't significantly deflecting the spring material, and the shear force isn't effectively doing any of the springiness. It's not adding to the stiffness or the the ability to move that spring in and out. That's entirely, when you collapse the spring or extend it, you're essentially twisting it. So if you want to think of it this way, what you're doing with a helical coil spring when you work it, imagine just having a strand of wire, a straight strand of wire, and twist it. It's actually, if you have a sizable length of wire, it actually becomes really easy to twist. And that's a torsional spring, right? Well, that's exactly what this is. So the wire is actually a torsional spring. So it's a torsional spring, but in this physical um, layout of a coil, you can take the torsional springy qualities of spring steel and put it into a translational instead of a rotational spring. Pretty neat stuff. So obviously, if torsion is a big deal for helical coil springs, we would be interested in maximum shear stress, and in particular for static loading. So we're looking at stresses in these helical coil springs. We're going to start with static loading and identify the maximum shear stress. And here we've got a couple of things here, K sub S, for instance. So really you'd start down here. So this would be step one, identify C. And this is the nominal diameter, nominal coil diameter. And this is the wire diameter. So if you have a spring, right, nominal coil, whoops, nominal coil would be from the centers. So this is D. That's the coil diameter. And of course, this is the wire diameter. So you'd start by calculating the constant C. From that, you would calculate the spring constant stress concentration factor. And then finally, you can get the maximum shear stress using K sub F, K sub S, sorry. There's a bunch of intermediate equations. They're not useful. So these are so for static maximum shear stress, these are the three equations you need to use. You can ignore all the other intermediate equations. So now we're looking at fatigue loading, and this looks like the same equation, except now we have a K sub B. So again, you'd start with C equals D over D. That's step one. Step two, your fatigue stress concentration factor, and then step three, the maximum shear stress for fatigue. So again, you kind of work from the bottom up. And again, there are a bunch of other equations that don't add much. Please ignore them. So this is the meat and potatoes of the of this stresses section on maximum shear stresses. As far as deflection goes, you can pretty well ignore this and skip right to that. And so we have a couple things here. This would be the actual, Y is the deflection. So this is the deflection. Let me do a better job of that. This is the deflection, Y. And the stiffness, remember K, generally speaking, the stiffness, K equals some force over some displacement. So in this case, we have a definition based on the material properties and the geometry of the spring. So this is the stiffness. This is the stiffness. And let's see here, you can verify the units of this, but G here is the shear modulus. And we're using that because it's primarily in torsion, the wire is primarily in torsion. And if you don't have G given for a material, you can find it using the Young's modulus and the Poisson's ratio. This is the Poisson ratio, and that's for isotropic materials. So here we have up here we have a approximate value for the spring stiffness. I drew this on the previous slide, but here you can see what the nominal coil diameter and wire diameter, it's a little clearer on this one, what those values mean. Ends, this is, you really need to read the, there's a little accompanying text blurb over here in figure 10.2 that you should probably read. They're only showing the right-hand end. So only right-hand end is being shown. Let me move that over a little bit. Oh, that still ran off. So it's assumed that both ends are the same. So this is not an end. You notice that it's a little squiggly right here. So the spring continues. Same thing here, it's a little broken edge. That means the spring is continuing, and that it would have this end over here. It would have the same end on this side. Same thing, this one would have the same end on this side. This one would have the same end on this side, and likewise, same end on this side. Right? Okay, so we've got four definitions. We have plane. That means pretty much nothing's been done to the end. We have squared, which means that the last part of the last coil has been bent to be flush, perpendicular to the, or parallel to the surface that it's mating up to. Then we have squared and ground, where it's been ground down to include almost a full footprint. So squared and ground, this is almost a full contact footprint. Right there, that's squared and ground. And plain ground just means that they ground off the last little bit of the last coil. So it used to be here, and the part sticking out they just ground off. If you grind a little deeper, then you get to squared and ground, which is C. But just plain end ground is a little less grinding and much less contact footprint. So a lot of the formulas use N sub A, number of active coils. That's what N sub A is. And we can see the number of active coils. Here's the four different types. So if we just start here with plain, all the coils are active coils. Now we have end coils and total coils. So we have the formula here. Total coils is the number of active coils plus the number of end coils. So from this we can back out the number of active coils. So if you count the number of coils and you know how what the end conditions are, then the goal here is to calculate what the number of active coils are. Now the inactive coils aren't actually contributing to the springiness or stiffness. So inactive coils do not contribute to the springiness. So let's look at the previous slide here. For instance, this last, I'm going to get rid of this. This last coil right here, that's not contributing to the springiness. That's just material that's directly in contact with the surface. That last coil is doing nothing as far as springiness. All it's doing is helping locate the end of the spring on the mating surface. So that's an inactive coil. So that end coil, these end coils can be inactive coils. And so these are, you could call them end coils or inactive. So that from that we can back out the number of active coils. There's also free length. This is P here is the pitch. That's how many coils per, that's how many coils per inch or meter, whatever units you're in. So this will tell you what the free length, so that's important, know what the free length L naught is. The solid length is if you collapse the spring so all the coils are touching. So L sub S is a condition where at that length all the coils are touching. Obviously, you won't get any more springiness out of that thing once you collapse all the coils. And then lastly on this table, here's the pitch based on the free length and the number of active coils and all that sort of stuff. So you can actually calculate a lot of stuff here. You can calculate the number of active coils, free length, solid length, and pitch. And that's used in several different equations. So the main thing is to identify your end conditions. So here are your end conditions. And then work through the table to calculate N sub A, L naught, L sub S, and your pitch P. Set removal or presetting of a spring. This induces a useful residual stress in the spring material. So you actually, when it says here the spring is made longer than needed, it's manufactured longer than needed, and then compressed to the solid height, and that intentionally yields it. So that sets the spring to the final free length. So once you yield it at the solid length, if you go back to the solid length again, you're not going to yield it again. It's already seen that, you've already absorbed that yielding on the first set, right? So this way the spring is more stable. So in case you do overload the spring, it's not going to suddenly change its dimensions on you. It's already been preset. It's already had the yield removed at the solid length. And now if you reach the solid length again, the spring doesn't care. It'll go back to where it was after the presetting or set removal process. So you can, this is generally as a rule of thumb, 10 to 30% of the initial free length could be removed. And you probably don't want to do this for springs and fatigue. So not recommended for springs subject to fatigue loading. Compression springs, these are also helical coil springs, can also be compression springs. That's what we're talking about with the solid length. Here it's defined, one coil against the other in this first bullet here. Obviously this spring takes on a very different characteristic of the solid length. We're just topically covering this, but when you have a compression spring, often you want to use a guide rod for long compression springs. That's to prevent the spring from buckling, squirming around. And this is also often done for soft springs with a lot of pre-compression. And the reason for that is to have a fairly constant force regardless of the spring compression condition. So if you take a really soft spring and pre-compress it, and then just work it a little bit around that pre-compressed state, it can become virtually a constant force mechanism, which is kind of neat. You can also use this arrangement with compound springs. Here's one shown below. Compound springs, compound slides. This one in particular has a very nonlinear behavior, so this gives you a non-linear compressive behavior. In particular, this is the softer spring. So initially the soft spring compresses, and then eventually the stiffer spring kicks in. So this would be the first thing that engages, and then the second thing. And this will give you a nice soft initial stiffness, and then when you reach the solid length, all of a sudden the system gets a lot stiffer and tries to return the mechanism a little bit more quickly. Critical deflection for stability. Okay, so this is we're talking about, when we talk about critical deflection for stability, we're really talking about a buckling type of instability. Again, in the previous slide, you can combat that with a guide rod. So this is a guide rod. And there's another guide rod in here. And in this case, these springs would almost certainly buckle under any significant deformation, except that we've added a compound guide rod system so that they're not capable of buckling anymore. The guide rod prevents it. So typically you're going to do that. You could also sink these things down into a cylindrical depression so that it doesn't have to be an inside guide rod. It could be an outside guide sleeve. But this gives you this equation here gives you the critical deflection, Y sub CR. So when you reach this deflection, the compression spring will buckle. So at this, it buckles. Again, you're going to have to kind of work from the bottom up. This is the overall formula given first, but you clearly need to calculate this first. So this would be step one. And then you would calculate this second and this third. But the overall equation still is Y critical for that's essentially the deflection that causes the compression spring to buckle. We also have the end condition constant. This is just from table 10.2, and it accounts for the way in which the ends of the springs are supported. And this will give you the condition for absolute stability. So if you want a spring that just doesn't buckle, then it has a initial length or uncompressed length. Let's just check our definitions here. I'm going to go back a slide or so. Of course, OneNote's now taking a little while. The free length, L naught. Whoops, went a little too far. So if you design the spring with a free length less than 2.63 d over alpha, so this is the free length, and this is a design condition. For compression stability. So if you don't want to use a guide rod or a guide sleeve and you have a compression spring and you want to make sure that it doesn't buckle, you have to keep the free length less than 2.63 times the coil diameter, nominal diameter, divided by the end condition constant alpha. The book has some common spring steels. This C here is carbon content. We have some high carbon, believe it or not, even though this is in percentages, carbon that's, these are generally high carbon steels. Hard drawn wire, oil tempered wire, music wire, chrome vanadium wire, chrome silicon wire. Most springs you see will be hard drawn wire because it's the cheapest. And most of the springs in daily life, accuracy and life aren't particularly that important. But as you go up in importance of application, you'd go up the scale for more and more expensive. So typically these are getting more expensive as you go this way. Strength with small diameter wires, strength is a function of diameter. And we have values of A and M on table 10.4. So this is the ultimate tensile strength as a function of diameter. And we can get these values of A and M from table 10.4. So here's this equation again, estimating the tensile strength. And we have our different types of wire, our materials here. Let me pick a different color. Since they're using red, I'll use blue. So based on a material and the diameter, you can a diameter range. These are considered small diameters. So these are small diameters. Lowercase d. These are wire diameters. And you can get M. Here's M. And here's A in 2 different units. And as you can see, the relative cost here, we've got hard drawn is the cheapest, and then it gets more expensive from there, as I mentioned in the previous slide. But this is a good estimate of your tensile strength for these small diameter wires. If you want to estimate the torsional yield strength, you've got a range of all this sort of stuff. You can kind of ignore that and use this for the torsional yield strength. It's a shear strength to, let me back up a second here. Let me back up here. We got shear yield strength is going to be needed. So that's what S sub SY is. S sub SY is the shear yield strength. And they're giving a couple of conflicting things here. You can kind of ignore this. Sorry. And what this results in is that. But in the example problem, they're using S sub SY is 0.45 S of UT, which is kind of in between these values. So they give you a range and they pick something in the middle as an approximation. That's in one of the first example problems. Again, here table 10.5 is a pretty useful table. Gives you the elastic limit percent for this is what we were just looking at previously, percent of SUT. Most importantly, they give you E and G, the Young's modulus and shear modulus. And you notice these percentages are ranges, right? So it really depends on the particular batch of wire you got. Probably pick something in the middle. So if it says 45 to 50, pick 47 and a half. 65 to 70, pick 70. So that's basically, and they're giving this to you in 2 different ways. There should be they're giving you in tension and torsion. So this would be for S sub y, this would be for S sub sy as a percent of SUT as percent of SUT. And there's just some variability in the diameters of these wires. There's some variability in materials and processing. So they're giving, instead of locking it down into an exact percent, they're giving you a range just to let you know. Again, there's also some maximum allowable torsional stresses in table 10.6. They're giving it to you in two ways: before the set is removed and after the set is removed. And this is as a percent of maximum, right here, as a maximum percent of tensile strength. So that's a percent of SUT, just to clarify that. And this is the, again, maximum allowable torsional stress. So you can go back to slide 3 or 4 or whatever it was and calculate your torsional stress, and then compare that to this fraction, this percent of the ultimate tensile strength, to see if your spring is going to survive. Okay, example 10.1, definitely go through this. You definitely want to go through this on your own. We're going to go through it kind of quickly. It's asking for a lot of stuff. Estimate the, here, let's go through it. A, estimate the torsional yield strength of the wire. Estimate the static load corresponding to the yield strength. Estimate the scale of the spring. What the hell is that? It's the first time they've mentioned scale. Well, okay, what they mean there is scale. Whoops. They're asking for estimate the stiffness of the spring. I don't recall hearing them use the word scale in the body text of the chapter, and I've never heard it, the spring stiffness referred to as the scale of the spring. So I'm not sure what that's doing there. It's a little confusing, but let me just straighten that out for you. Part C is estimating the spring stiffness. Okay. Estimate the deflection that would be caused by the load in part B. So this is the load to yield, right? And then estimate the solid length of the spring. That's L sub S. What length should the spring be to ensure that when it's compressed solid and then released, there will be no permanent change in the free length? That's a fairly complicated thing to ask. Given the length, you know, thinking that through part F, you would have to calculate what the initial length and solid length would be and what that deflection is, and keep that deflection less than the deflection corresponding to part D. So if you have a deflection that would cause yielding, part D. So here, let me explain part F before we go on. So in part D, you have a deflection to yield it. And then in part F, you need a, what length should the spring be so it was a compressed solid? There will be no permanent change in the free length. In other words, i.e. no yielding. So if we already know the deflection to yield this thing, then L naught minus LS needs to be less than whatever the deflection is to yield. The answer to part D. Right? So the total possible spring deflection is L naught minus LS. So the free length minus the solid length. That's the total possible spring deflection. And as long as you keep that less than the deflection required to yield it, then you've solved for part F. And then given the length found in part F, is buckling a possibility? And what is the pitch of the body coil? That last one, you're just applying a formula. So they're starting off with estimate the torsional yield strength of the wire. If we go back in a couple of slides here, um, we've got, well, it's quite a ways back. A lot of this stuff over here is based on SUT. So the first thing we need to do is figure out SUT. Go forward a little bit to this example, and that's exactly the first thing that they do. They find SUT. They're using, just to let you know, table 828. They're getting wire diameter. And then they're getting A and M from table 1024. So this kind of gives you a roadmap of this blurb right here is a roadmap of tables and equations to find SUT. And in almost every spring application that you would be doing for this chapter, finding the ultimate tensile strength would be one of the first things. And then here they're using S sub SY is 0.45 SUT. As I mentioned before, that's in this slide here. Where is it? They're using something in that range. If we look at 10.6, they got music wire, so they've got maximum percent of tensile strength. They're using this number here, 45%. Same deal. But let me go back just real quick. So maximum allowable torsional stress. So this is going to be your S sub SY, right? A before and after set removal. So this is the one they're using right here. And they're plugging in their value of ultimate tensile strength and getting an answer for part A, the torsional yield strength of the wire. Part B, let's see what they're asking for in part B again. Estimate the static load corresponding to the yield strength. Okay, so we've got important text coming in. No. Okay, so anyhow, sorry about that. I've got it on vibrate. You probably still heard it. Anyhow, we're going to go back to some of the earlier formulas here, equation 10.6 and 10.7. Well, first, like I said before, item 1 for finding this is to find C, and then find your concentration factor, and then if you want to know, since we want to know the force corresponding to yield, we solve 10.7, we rearrange 10.7, and since it's going to yield, we're saying the actual shear stress is SSY, so it is yielding. And solve for F, and you get this monstrosity here. Let's look back at equation 10.7 just to orient ourselves. I'm going to go back a couple slides here, several slides. Trying to find equation 10.7 here. There it is. Okay, so this is what they're looking at here. Sorry for flipping around. They're assuming, in this case, what's interesting is they're assuming a fatigue application. So it's not clear from the example why they're using the fatigue criteria. They could have, let me go back here. They could have decided to use this static. And because they didn't specify, if I were to ask you this question and you used static, I would not take any points off. Let's just look at the problem statement again. Nowhere in this problem statement does it say that this thing's under a fatigue condition, that it sees a lot of cycles. Obviously, a lot of springs see a lot of cycles, but not necessarily. So it seems like in the absence of information, they're taking a worst case scenario and assuming that it's going to fail in fatigue. I would have, if I were to rework this problem myself, I would have used, based on the wording, I would have used the other formula for static, which is way back here. I would have used this. In what example problem? That's page 4 versus page 20. Page 4. So I would have used this in part B. Let me see what I'm dealing with here. Part B of example 10.2. So when you read that note, I've made this, I'm already like 16 slides ahead. Let me make sure no, example 10.1. Let me correct that. Example 10.1. I would have used this. This was used in example 10.2 without any explanation of why the fatigue criteria was used over the static as per previous slide. Like I said, I would have used this instead. So just keep that in mind as you go through this, that for some reason, in an unexplained fashion, they're using the fatigue version. This is the fatigue version. Part C, number of active coils. You have to go back to the given for the problem. There's 12.5 total turns. So for part C, this is, you're going to need to know the end condition and the how many total turns there are. So the ends are simply squared, so they're not ground at all, they're just bent over to be flat to the surface. And you need to go to the table, it would be table 10.1, and that'll get you the total coils minus the end coils is the number of active coils. So this formula here is number of active coils equals total coils minus end coils. So if you look on that table, you have two end coils on a squared end that you assume both ends are squared. So those two coils are inactive. So that gives us 10.5 total active coils. If what we're looking for isn't the scale, it's the stiffness. If you look up that formula, you're going to need a couple other things besides active coils. You're going to need the modulus of rigidity, which is you can get from table 10.5. And they give you the coil diameter, nominal coil diameter. Let's go up here again. The outside coil diameter is what they give you actually. So that's not the coil, that's not the nominal coil diameter. So the actual nominal coil diameter is going to be different than that, which they put in here. So you have to subtract the, so if you have the outside coil diameter, in order to get the nominal is the outside minus the wire diameter. So that's what they're using there for D. So D is the nominal coil diameter. They gave you the outside coil diameter. So I'm just making a note here versus the given is outside coil diameter, and you need D, which is the nominal coil diameter. And the nominal coil diameter is just the outside coil diameter minus the wire diameter. And that's what goes in right there. They're going to find the C was what they're looking for. Again, this is a long example. They're looking for, okay, so we found the 6 scale of the spring. The next thing, D, so this is C, scale of the spring, make sure you're in the right units. D, let's flip back, estimate the deflection that would be caused by the load in part B. So they did get a load for part B, even though I disagree with it. And the deflection, you have this, F equals ky or kx or whatever else. And if you want to know the deflection, you just solve for y. And the force in this case is the force to yield it. And that's pretty straightforward for calculating D. For part E, let's flip back and see what we're looking for. Estimate the solid length, L sub S. This is from the table. Number of total coils plus 1 times the coil diameter. That's just a table lookup. Identifying your formula by the correct number of coils, or I'm sorry, the correct end condition on the table, and then knowing that L sub S is the solid length. And then we're looking for a free length. That this is part F here. You notice that this is the free length. This isn't a formula in the book. This is what should the free length of the spring be? I can tell what question F was by looking at this formula. What should the free length be such that the spring won't yield when you compress it to its solid length? That's essentially what they're asking in F. That's not how they word it, but what length should the spring be to ensure that when it's compressed solid and then released, there will be no permanent change or presetting in the free length? That essentially means that if you compress it, you don't reach the static spring, or the yielding deflection. So we calculated Y was calculated in part D as the deflection required to yield it. So if the total free spring length is the solid length plus Y, then there's no possibility of yielding it. That's exactly what they do here. So you can load this spring right up to the yield point, and then you'll hit the solid length, and you can't compress the spring anymore, so it never yields. For a buckling, the last part, table 10.2. You know what? I'm going to back up. This is tricky right here. F. If it's not explained, it's not really especially clear because this formula is not in the book. You just have to think this one through. That they asked you to find the deflection required to yield the spring, and now what should the free length be so that you can't yield the spring, right? It's sort of a tricky little question, but once you see it, you're like, oh yeah, well if Y is the deflection to yield it, and we don't want to go past Y. The way to stop the spring from compressing past Y is to make the total length Y plus the solid length, and then when you get to the yield condition, you're already at the solid length, and there's no possibility of going further, so your spring never yields. All right, last part, you have to look up equation 1013 and 10.2. That's that formula that was with your end condition alpha, and you have your, that was just a couple slides back, this formula here, L naught, that's the stability condition, and you have to look up alpha from the table. Let's go ahead and see if I can find that. Let's back a couple. I'm just going to curious. That's not it. Constant alpha. They're using 0.5. If we go forward, they don't really say. What's interesting is they don't really tell you. They're using 0.5 for alpha, but in reality they don't make any mention of why they picked 0.5. Whoops, that's all ran off the end of the page. Let me redo that. So they made no mention. Whoops. From the way I'm looking at it, they could have picked, they didn't say the spring was supported between two flat parallel surfaces. They never made mention of that in the problem. So you could have assumed any of these in example 10.2. So I think they're just picking the least conservative. This would be the least conservative here. And let's see what we get here. And with the least conservative, you get 2.10 inches. And I think, you know, here they make mention of some tangentially of, you know, if alpha is going to be close to 0.5 and whether or not you need an inside rod and all that sort of stuff. I think if you had a little bit more clear definition of how the spring was mounted, yeah, you wouldn't need that discussion. And then pitch, this is again from table 10.1. So the moral of the story is here, be familiar with table 10.1 in particular. It was used in a bunch of these, right? It was used in part E, it was used earlier in the problem, but table 10.1 was used several times throughout this example problem. This example problem is probably 80% of what I'd ask you on a formula lookup type problem on the final. So definitely make sure you go through this example on your own again. Here's some recommended design conditions. C, this is just for a reminder, D divided by D. This is number of active coils, this Greek squiggly line. This is the percent overrun. So in other words, you want your maximum, you want about 15%. I believe what this says, you want 15% extra distance before yield. So if you know what your solid length is or your length to yield, you'd want about a 15% buffer zone. And the factor of safety at the solid height end sub s, that's described. And here's where they're working in the zeta, and that's all way too complicated. I'm not going to ask you that. It's interesting, but who cares? Don't care. I think everything before this in example 10.2 was pretty much the kind of stuff I was going to ask you. Make sure you go through example 10.2 and 10.3 as well. You'll be responsible for those. Here we are at the fatigue, critical frequency, fatigue, and modulus of rupture. They're only being treated topically, and we're skipping these examples. Same thing with this. We're only well, we're not covering this, so I'll take the X out. But here, let me circle the important part. Topically, example skipped. Topically, example skipped. And so in skipping, we're going to extension springs. One of the important things about extension springs like this, here we have some common hook types. Aside from that, there's oftentimes there's an initial load required to separate the coils. So the force versus deflection curve will actually not start at 0. It'll have some initial force that's required to even to get the coils to separate. That's something I noticed from a student experiment, and I had a student in my vibrations class build a little vibration, mass spring type of test platform, and she was getting weird answers compared to her simulation, and we determined that the extension spring she was using started with fully solid length collapsed coils, and that there was actually a small amount of force required to even get the coils to separate. So all the other equations or stiffness plots in the book have you starting here, but in this case with these extension springs, often there's a pre-amount of force required to separate them. You can also use helical coil springs as torsion springs. Usually these have a guide rod to maintain alignment and prevent buckling. These things are everywhere. All sorts of different ends to these. But last time I saw one of these was on a Weber grill. They're actually used to hold the ash pan in place. When you push the ends together, the coil actually gets bigger in diameter, and you can slide it over a pole. So here we have a pole, and then you have your torsional spring, and when you flex these things in, the diameter gets bigger. Whoop. When you flex these in, D gets bigger. And then you can mount this thing over the rod and then release it, and it'll stick there. That's a pretty cool device, pretty simple, just a couple coils of wire, and it's adjustable. You just squeeze the spring open and it increases in diameter. You let it go and it clamps itself on. So sometimes these things aren't actually used like springs, they're used as clamps, placement devices. Again, this is off the leg of a charcoal Weber grill. I noticed they're using this simple element for that. These are that's a pretty long equation there, but just in case you need it, here's the deflection and spring rate and torsion springs. Probably will not have you be doing that calculation on an exam. It's pretty complicated, but they have, these ones are torque per radian and torque per turn, so just make sure you're using the right formula. Again, read the note. Perfect example of where you need to know where to look up the information when you need to know it. There There's a lot of other details in this that's not very adequately covered in the book, and more importantly, we don't have adequate time to cover it here. There's a lot more information that's in the book as well. Here's the one we're skipping. Static and fatigue strengths at torsional springs, mercifully skipped. Skip the example as well. A couple random springs here, Belleville springs. This looks like a washer, like a conical washer. So it looks conical washer. And they have a very nonlinear behavior. They have a snap through where they actually get less stiff. So you can also stack these things. So generally speaking, they look like this with some thickness. And you press on them, and eventually they'll snap through. Not spap through. They'll snap through, and that's what's happening here. Is the snap through, where the all of a sudden you get a negative stiffness. It's a highly nonlinear stiffness, and after it's done almost snapping through, obviously the stiffness will go significantly up. These things are usually stacked. You can stack them like this. That would be in series, or you can stack them like this. That would be in parallel. So if you need a stiffer Belleville washer, you'd stack them in like just one on top of the other. And if you need them softer, you could take them and put them up, same end to same end, like on the left. So this is series, this is parallel. Now I've heard of Belleville springs in my machine design class, and I've heard of them other places too, but I've never actually seen one. So it seems like every machine design book feels obligated to put these things in there, except they're pretty elusive. I've never actually seen one, and not sure if they're actually ever used for anything, but it is an interesting mechanical property. You take a linear material, and in this configuration, you can get an extremely nonlinear spring. It's good to know. We have constant force springs. This is just basically a roll of a steel strip spring. So if you need a constant force, this is like your a retractable dog leash. Conical spring. What's neat about this is that you can collapse it to its solid height as only a single wire diameter tall. So the whole thing will just lay inside its own footprint. Volute spring, same thing, except you're using a piece of flat material. This is super easy to form, and again, one of the things is as these coils go into contact with the ground, they become inactive coils. So this thing actually gets less and less stiff, but then it also collapses down to its solid height is just the width of the strip, which is compact. And I believe that's all there is. Yep, page 31. That's the last slide. That wasn't too bad. Again, it wasn't. This is meant to go along with the previous chapter. I normally would have covered both these chapters in one 2 hour and 50-minute session. So that covers 1 week of lecture between chapter 9 and chapter 10. Enjoy. I'll post this to YouTube and give me your feedback. I appreciate it. Bye.